Hello and welcome to our discussion on oxidation and reduction. These are simply a special kind of chemical reaction. So to start, let's review our 5 types of chemical reactions. Starting with the first one, you see that we have a compound and another compound, and they're both soluble in water. And on the opposite side, the lead is now bonded to the sulfate, and the nitrate has now bonded to the sodium. So you can see we've had a switch. This is a double replacement. Now, interestingly enough, double replacements are not redox reactions because there is no changing of electrons, and we'll see that here in a little bit. The next one, we're producing carbon dioxide and water, therefore we must be combusting something. The next one, we have one product, so that is synthesis. The next one, we have an element and a compound, and on the opposite side, the element has moved, the one that was by itself has moved itself into the compound, and the silver, which formerly was a part of the nitrate, is now on its own. This is a single replacement. And finally, we have one thing, decomposing, so this is decomposition. Now, if there are electrons that are transferred, we call these redox. Oxidation, reduction. And we shorten it a lot of times to redox. We keep track of what electrons are doing in a reaction by using what we call oxidation numbers. And I can't spell. In many cases, the oxidation number is the same as the charge if we're talking about ions, or when we are talking about ions. But if we're talking about covalent compounds, this is not the case. The covalent compounds, electrons are shared. So in that case, we have to consider electronegativity. Now, a quick review on electronegativity. Electronegativity is how attractive that atom is to other electrons. In other words, how sexy it is. And we all know that fluorine is people's sexiest man of the year. So, fluorine is the most electronegative. He is going to have the highest attraction. If he can attract those electrons, he ends up with, in a compound, he'll end up with a negative charge, partial negative charge. And that is what we're talking about when we talk about oxidation numbers. Okay? For instance, oxygen is the second highest electronegative element. He has 6 electrons. If he bonds with hydrogen, hydrogen comes along. Hydrogen has that 1 electron. He lets oxygen have it, and oxygen pulls on it much more tightly than hydrogen does. Therefore, it spends most of its time around the oxygen. I didn't do that very well, but hopefully you can see the electrons are here more. That's going to give this end a slightly negative charge, and this end a slightly positive charge, like a magnet pole. This is where we get the name polar molecule, because the electrons are not shared equally. And that is what's happening with oxidation numbers. We're just looking at where are the electrons hanging out. Okay? We have some basic rules. I just explained this These cases, we treat the electrons as if they belong to the atom. In other words, the more electronegative will have a hold on the electron. So basically, a redox reaction is any reaction where an element has a change in their charge or oxidation number. Our basic rules: elements by themselves are always zero. That is because protons are going to be equal to electrons in a neutral atom. An ion is always going to be equal to its charge. So if you have iron 3 is going to have a +3 charge. If you have sodium's in the first family, they all have a +1 charge. That's their oxidation number. Oxygen is always going to be -2 unless it's in a peroxide, when it would be -1. Hydrogen is always a +1 if it's in a covalent compound. In other words, if the hydrogen's bonded to a metal, then it would be -1. Fluorine, because he is the sexiest element, is always a -1. The sum of the charges have to add up to 0 for compounds, just like when we did ionic compounds. In covalent compounds, the electrons being shared still have to add up to 0. Polyatomic ions, which are not a compound, they're just an ion, a group of ions, always add up to their charge. So let's practice this. Oops, that didn't work very well. All right. Potassium, it's element first family, family 1A. So he's always a +1. Now when I do oxidation numbers, I write the charge of the element on top and then the whole charge for that element on the bottom, you'll see. Oxygen, we just said, was always -2 unless it's a peroxide. -2, but there's 4 of them. Our total here is -8. Our total for the potassiums, there's only 1, so it's a +1. If this has to add up to 0, we now have a math problem. 1 plus what -8 equals 0? Well, that has to be a +7. So manganese and potassium permanganate has a +7 charge. Tetraphosphorus hexoxide, another element. We know oxygen is a -2. There are 6 of them, so we have a total of -12. We have to add up to 0. So this phosphorus has to be worth 12 positive, and 12 minus 12 is 0. There are 4 phosphoruses, so what is each individual phosphorus going to be? Well, 12 divided by 4 is a +3. Sodium oxalate. Sodium is a +1. There are 2 of them, so we'll say that as a total +2 for all the sodiums. Oxygen's a -2. There's 4, so we'll say it's a total of -8. 2 plus what -8 equals 0? That's a +6. There's 2 carbons, so each one of those guys is a +3. Now, this guy's a little bit more complicated. We know that NH4 by itself has a +1, and there are 2 of them, so we have a total of +2 for this compound for this part. If we look at the rest of it, oxygen's always a -2, so that's a -8. Hydrogen's going to be a +1. So now 2 plus 1 plus what? -8 equals 0. Well, that'll be a +5. So phosphorus here has a +5 charge. Now, that didn't solve my ammonia. I'm going to pull the ammonia off to the side here. Remember that he has an overall a +1 charge. If he's a +1 and hydrogen's always a +1, that means this nitrogen has to be a -3. -3 plus 4 gives us +1. Okay? Now that you have a background on oxidation numbers and how to figure them out, let's talk about what happens in a reaction. First of all, you can't have oxidation without reduction. The electrons have to go somewhere. And I'm going to teach you a little mnemonic. That mnemonic is oil rig. Oil stands for oxidation is losing. And what is it losing? It's losing electrons. Rig, I'm going to rewrite over here, means reduction is gaining electrons. Okay? Oil rig. Oxidation is losing electrons. That means the charge is going to increase. That's, you see it here losing, you think, oh, that means the charge will go down. But remember, electrons are negative, so if we're losing electrons, our charge will go up. So that's another thing to think about. The charge will increase if it's being oxidized, and it will decrease when it's being reduced. This actually harkens back to the alchemists. They would take something, for instance, iron. Iron by itself has no charge, but if it is mixed with oxygen, it will oxidize to either a +2 or a +3 state. So its charge went up, and that's where the term oxidation comes from. Nowadays, we know you don't have to have oxygen involved in order to have oxidation. But early on, we had metals that were oxidized to their to the compounds that were oxides of the metal, and that's where that comes from. So, since oxidation means losing electrons, reduction means gaining electrons. An oxidizing agent, therefore, is the thing that causes oxidation to happen. So an oxidation agent is actually the element or the compound where the element's in that gains the electrons. It's the opposite. And the reducing agent is the element that loses. In other words, whoever's being oxidized, he's the reducing agent. And whoever's doing the reducing is the oxidizing agent. It's kind of silly. I really don't like it at all. But that's okay. It's not my choice. All right, here are some some equations. Let's figure out who's being oxidized and who's being reduced. Oxygen has a -2 charge. Hydrogen has a +1. This hydrogen has a +1. So now we're sitting at a +3, +1, a +4, -2. We have to add up to 0. So what does this carbon have to be in order for this equation to be true? He would have to be a -2. Okay? So carbon here has a -2. Oxygen here, he's a element, so he's going to be a 0. On this side, oxygen now is in a compound, so he's a -2. We have a total of -4, so what does carbon have to be? He's a +4. And in H2O, we have a +1 and a -2. So, whose charge increased? That means he lost electrons. The charge that increased was carbon. Carbon went from a -2 to a +4. So he lost 6 electrons. Okay? He was oxidized. So this is what was oxidized. The carbon was oxidized. So the ethanol or the methanol here is our reducing agent. Now, oxygen's charge went down. So oxygen is what's being reduced. So he was reduced, which means oxygen is the oxidizing agent. All right, let's try another one. Copper here is going to be 0, -2 for the oxygen, +1 for the hydrogen, which makes nitrogen a +5. Now copper's bonded to 2 nitrates. Each nitrate has a -1, so copper must be a +2. There are 6 oxygens, so there's a total of, there's 3 times 2 is 6, a total of -12. We have a +2 from our coppers, so this has to be a 10. There's 2 nitrogens, so each nitrogen must be +5. This oxygen's -2, so this nitrogen would be a +4, and hot water is +1 - 2. So whose charge went up? Well, if you're playing along at home, you noticed copper went from a 0 to a +2. So copper was oxidized. Whose charge went down? Well, nitrogen here is a +5. It's also a +5 here, so that one doesn't really count. Oops. Let's just take that away. All right. So we went from a +5 to a -2. So nitrogen was reduced. This means that copper was our reducing agent, and nitrogen was the nitric acid was our oxidizing agent.